Good evening, students. In this lecture, we are going to see few more numericals on heat exchanger. Okay. I have already copy pasted the problem number 13 in front of you. Let's start to interpret the data. Our first job is to identify the type of heat exchanger. Is it parallel? Is it counter? Is it condenser or is it evaporator? The steam is condensed. So very first sentence tells you this is the problem belongs to condenser. So start drawing the diagram of temperature profile. Just I am sorry for the disturbance. Okay. So the steam is condensed means it is condenser. Now I will draw the temperature profile diagram for a condenser. And what is that? In condenser, the hot fluid is changing the phase, and during phase change, temperature remains constant. So hot fluid is changing the phase. So temperature of hot fluid remains constant. So it is shown by a horizontal line. That means TH1 and TH2 is same at atmospheric pressure. So you must know at atmospheric pressure what is the condensation point of steam. At atmospheric pressure, steam get condensed at 100 degrees Celsius. So TH1 is 100 degrees Celsius and TH2 is also 100 degrees Celsius. This is not given in the problem, but you have to understand because at atmospheric pressure, the steam is condensed always at 100 degrees Celsius. So TH1 and TH2 is 100. The type of heat exchanger is shell and tube type of heat exchanger using water as a coolant. So just make two columns. Hot fluid, that is steam, and cold fluid. Water is used as a coolant. Coolant means cold fluid. So cold fluid is water. During condensation, water is heated from. So what is to be going to be heated? Cold fluid. So TC1 is 28 degrees Celsius. TC2 is 48 degrees Celsius. This is for cold fluid. Now you are saying, sir, both the fluids are entering in the same side. It is type of parallel flow heat exchanger. But nothing is mentioned whether it is parallel or counter. Remember, condenser or evaporators are the heat exchangers. These can be operated in parallel flow or counter flow. The effectiveness of that heat exchanger does not change. So you can draw parallel flow heat exchanger or counter flow heat exchanger for condenser or evaporator. It doesn't matter in the final result. So here I have shown as both the fluids are entering from the same side, that is parallel arrangement. So TC1 and TC2 is written. TC1 is 28 and TC2 is 48. Now you know all four temperatures. If you know all four temperature, which approach you need to use? LMTD or effectiveness NTU? LMTD approach, because that is the most easiest way to do it. Water flow through the tubes. Water flow through the tubes. So this is inside fluid. Inside the tubes. Okay, water is inside. So naturally steam comes outside. Okay, water is inside and steam is outside. Now size of the tube is given. ID means inner dia. D is 2.6 centimeter. 2.6 centimeter. So it is how much? 0.026 meter. Then DO is given as 3 centimeter. 3 centimeter means 0.03 meter. Length of the heat exchanger 2.5 meter. Flow rate of water. Water is cold fluid. So m dot of C is 30,000 kg per hour. 30,000 kg per hour. Convert it in second. So divide by 3,600. It becomes as 8.3333 kg per second. Okay. Next, coefficient of heat transfer on steam side. Steam is which side? Hot side. So H, and that is outside. So HO is given as 8000 watt per meter square Kelvin, and water side is how much? 3000. So water is inside the tube, so HI is 3000 watt per meter square Kelvin. Neglecting the other resistances. Other resistances means what? The conductivity value for the tube is not mentioned, so naturally neglecting tube resistance. Why? Because the conductivity value is not given for the tube, so I have neglected that resistance. Calculate the number of tubes required. So what is the required answer? Required answer is number of tubes. Now we'll go for the solution. Now whatever the problems we have seen till now, there was no instance where the number of tubes are asked, or there is no formula we have seen where the number of tubes n are included. So how to calculate n? Remember, if I will know a total of the heat exchanger, and if I know area of a single tube, that is AI, so n into area of a single tube, that becomes area total of the heat exchanger. Area total of the heat exchanger. So if I know A total and if I know AI, then I can get the value of small n, okay, easily. So let's start. As 4 temperatures are given, we can use LMTD approach. So Q is equal to U A theta M. In this formula, and there is UI AI theta M, there is U0 A0 theta M. Now, as the dimensions of the tubes are given, you have to use either this formula or either this formula. Don't use a generalized formula because dimensions are given: inner diameter, outer diameter of the tube. So inner area is also we can calculate, outer area also we can calculate. So you are having two options in front of you, either second formula or third formula, okay? Don't use this generalized formula, okay? First one. Now, before this, we have solved the problem on the basis of inner area. So this time we will try, as I promised in last lecture, okay, we have solved two problems on inner area. This problem will solve by on the basis of outer area. So I will take Q is equal to U0 A0 theta M. If I want to know A0, that is outer area of the heat exchanger, okay, outer area of the heat exchanger in totality, what to do? So here I will write A total is equal to N. As I have selected on the basis of outer area, I will write here A0. Okay, A0. Because I have selected on the basis of outer area. If I have selected on the basis of inner area, I can write here AI. Okay. So make the change accordingly. Now, if I want to know this A0, I must know Q, I must know U0, and I must know theta M. So I think all these three things are unknown to us. So let's start doing calculation. How to calculate Q? M dot H, CPH, TH1 minus TH2. That is on hot side. This is on cold side now. M dot C, CPC, TC2 minus TC1. Okay. I have written the heat balance equation for heat exchanger. Now what is given? I think cold side data is available. Full data is available. So I can use this combination. Okay, to calculate Q. So Q is equal to M dot C. What is M dot C? 8.4 times 3. What is CPC? Specific heat. What is cold fluid? Water. For water, they have not given specific heat. So as water is a standard fluid, we must know what is the specific heat. It is 4.187 kilojoule per kg Kelvin, but when you are putting, you have to put it in joule. That's why 4187 into TC2 minus TC1. What is TC2? 48 and TC1 28. So 48 minus 28. So the answer of Q comes around Just a minute. Six nine seven eight 6978 30.54 watt. That I have already calculated, that I am writing in front of you. So Q is this one, 697830.54 watt. So I got this question mark removed. So Q is known to you. Now the next part is to get the value of U0. Now what is the formula of U0? 1 upon summation R. Here instead of AI, now you have to take UO because AO, because we are calculating overall heat transfer coefficient U on the basis of outer area O. So in the formula, instead of 1 upon summation R AI, we need to write 1 upon summation R A0. Okay. So now next, summation R A0 is equal to, I will write first summation R formula, 1 upon HIAI, that is inside, plus fouling resistances are not mentioned. So conductive resistance now, natural log of Rho upon Ri upon 2 pi KL plus 1 upon HO AO. Outer fouling is also not mentioned. So these are the three resistances in series: inner convective, across the tube conductive, and outer convective. So only three resistances are there. If fouling is on inside and outside, two more resistances are added because of fouling resistance, but fouling factors are not given, so we have neglected that resistance into A0. Now as the value of thermal conductivity is also not mentioned, neglect this middle resistance. Now what is summation R A0? Multiply to each term A0 upon AI into 1 upon HI plus 1 upon HO. So let's calculate A0 and AI. So A0 is equal to pi DOL and AI is equal to pi DIL. Just put the values. Pi DOL pi into what is DO? DO is 0.03 and what is L? L is 2.5. What is DI? 0.026 and what is L? 2.5. If I will calculate AO and AI, AO comes around 0.2356 meter square and AI comes at 0.2042 meter square. So A0 upon AI, if I will calculate 0.2356 divided by 0.2042, it comes around 1.1538. Now I will go for summation R A0 is equal to A0 upon AI is 1.1538 into 1 upon, what is the value of HI? HI is 3000 plus 1 by HO. What is the value of HO? It is 8000 for outside fluid. 8000 and outside is what? Steam. So for steam it is 8000. So if I will calculate it, summation R A0 comes at 5.096 into 10 raised to minus 4. Why we have done the calculation of summation R A0? To get the U0. Look at here. So if I take the reciprocal of this summation R A0, I will get the answer of U0. So U0 is equal to reciprocal of this 5.096 into 10 raised to minus 4. The answer of U0 comes around 1962.32 watt per meter square Kelvin. Now this question mark is also over. Now only remaining is LMTD, theta m. So for theta m, I require theta 1 and theta 2. What is theta 1? Theta 1 is TH1 minus TC1. TH1 minus TC1. And what is theta 2? TH2 minus TC2. Just put the values. TH1 minus TC1, 100 minus 28. 100 minus 28, and TH2 minus TC2. TH2 is 100, TC2 is 48. 100 minus 48. So 100 minus 28 means 72 degrees Celsius, and this becomes 52 degrees Celsius. So theta m is equal to theta 2 minus theta 1 divided by natural log of theta 2 by theta 1. 52 minus 72 divided by natural log of 52 by 72. So the answer of theta m comes at 61.45 degrees Celsius. So I think this question mark is also over. Now I will get the answer of A0. What is A0? Q upon U0 theta m. A0 is Q upon U0 theta m. So what is the value of Q? Q I got as 697830. 697830.54 divided by U0. How much it is? 1962.32. And what is theta m? Just now calculated 61.45. If I will solve this, A0, that is A total, A0 that is A total, I am getting it as 5.7870 meter square. But we know that A total is equal to N into, as I have taken based on outer area, A0 for single tube, A0 for single tube. What we have calculated, A0 for all the tubes, okay, for all the tubes in cell and tube heat exchanger. So A total I am knowing 5.7870 N, and what is the area of outer tube single? Look at here, A0. This is the area O of a single tube, 0.2356. 0.2356. So from this N is equal to 5.7870 divided by 0.2356. That comes around 24.56. But tubes are not partial or not in fraction. So just rounded it to nearest whole number. It is 25. So this one is your answer. So in shell and tube type of heat exchanger, there are number of tubes. So what you are getting by formula Q is equal to UA theta m, UI AI theta m, or U0 A0 theta m is the area of total heat exchanger, of total number of tubes. So if you know the area of a single tube, and if you know total area of the heat exchanger, just by taking a ratio we can calculate number of tubes. Okay, for tube in tube type of heat exchanger there is only one tube, but in case of shell and tube type of heat exchanger there are number of tubes. So this is the way by which we have to calculate number of tubes. Now we'll go to the next problem, and that is problem number 14. I will cut it for you. Now let's write the data. A steam condenser, again it is a condenser. So in condenser, hot fluid is changing the phase, means temperature for hot fluid remains constant, TH1 and TH2. And for cold fluid, you can show in parallel flow or counter flow, it doesn't matter. I will show in parallel flow mode, TC1 and this is TC2. Temperature difference between these two is called as theta 1 and these two is called as theta 2. Okay, so this is the temperature profile diagram for condenser. Condense 0.76. Okay, I will make a two column. One is hot fluid column and other is cold fluid column. What is condensing? Steam. Steam is condensed means that is hot fluid for which temperature remains constant, TH1 and TH2 equal with cooling water. So cold fluid is what? Water. Entering at 20 and leaving at 65. So cold fluid ही गर्म होगा from 20 to 65. So TC1 is 20 and TC2 is 65 degrees Celsius. So TC1 is 20 and TC2 is 65. Size of the heat exchanger is 0.17. I am writing it separately because it is nothing to do with hot fluid and cold fluid. So it is 0.17 meter square. Overall heat transfer coefficient is 3400. Please delete this statement. It is wrong because in this problem they have asked calculate the overall heat transfer coefficient. So how it should be given? It is by mistake. Please rub this statement or neglect this statement from this problem. Just cut it, okay, or drop it. Calculate the overall heat transfer coefficient. So what is asked to calculate? Required U. So how it should be given, na? You can easily understand. So this is a wrong statement. Please remove it. So required answer is U. Saturation temperature of steam. Now what is meant by saturation temperature? The temperature at which phase change occurs or condensation occurs for the steam, that is given as 95.6. So TH1 and TH2 are equal temperatures at which phase change occurs. So TH1 is how much? 95.6 and TH2 is also 95.6. Now HFZ means latent heat of steam. Steam is hot fluid, so I will write HFZ is equal to 2270 kilojoule per kg. So HFZ is equal to 2270 into 10 raised to 3 because we don't want kilojoule value. I will convert it in joule multiplied by 10 raised to 3 joule per kg. What is latent heat? Latent heat means during the phase change process, that is called the heat energy called as latent heat. So here hot fluid is changing the phase. So latent heat they have mentioned. HFZ is 2270 into 10 raised to 3 joule per kg. And what is asked to you? Overall heat transfer coefficient. So again check which approach we can use. All temperatures are known to you. We can use the approach of LMTD. If 3 or 4 temperatures are given, LMTD approach. If only 2 temperatures are given, NTU or effectiveness approach. Okay. So we'll go for the solution. U. So Q is equal to U A theta M or UI AI theta M or U0 A0 theta M. So three options are available to you. Which one we should use? Let's check the tube dimensions are given or not. In this problem they are not given. So this option and these options are automatically cancelled. Only this option is coming into picture. So if I want to know the value of U, Q is equal to UA theta M, I will place the question mark on this and this. So area is already given in the problem. So I think this is known to you. Instead of question mark, it is tick already. So only unknown is Q and theta M. Now remember, in case of condenser or evaporator, in case of condenser or evaporator, there is no sensible heat inward. There is a latent heat inward. Okay. So whenever latent heat is there, then the formula of Q is m dot into HFZ. M dot into HFZ. It is not m dot S CPS TH1 minus TH2 or it is not m dot C CPC TC2 minus TC1 for the fluid for which phase change occurs. Remember, in case of condenser or evaporator, wherever the phase change occurs, for that particular fluid you can use this formula. So this is applicable only for phase change fluid where latent heat is inward. latent heat is latent heat means what? HFZ is given. So in this formula, but which is the fluid in this case changing the phase? In condenser always hot fluid is changing the phase. So here I will write m dot h. Remember, in case of evaporator, cold fluid is changing the phase. Cold fluid is changing the phase. So in that case the formula of Q becomes m dot c hfz. But in this case hot fluid is changing the phase because this problem belongs to condenser. That's why here m dot h is coming into picture. Okay. So first I will calculate Q. Q is equal to m dot h. What is that m dot h? I think it is given, na? 0.76 kg per minute. That is hot fluid. I have not written. M dot h is equal to 0.76 kg per minute. So 0.76 kg per minute means how much? Point divided by 60 na, 0.0126 kg per second. Minute ka second karo, divide by 60. Now m dot h I know 0.0126 into hfz. How much it is hfz? 2270 into 10 raised to 3. So the answer of Q is 28753.33 watt. So I think the first question mark is over. Area is already known. Now only theta m is remaining. For to calculate theta m, I require theta 1 and theta 2. So what is theta 1? Look at the temperature profile diagram. Theta 1 is Th1 minus Tc1. And what is theta 2? Th2 minus Tc2. Th2 minus Tc2. So Th1 minus Tc1. 95.6 minus 20. 95.6 minus 20. And what is Th2 minus Tc2? 95.6 minus 65. Okay. So if I will calculate theta 1 and theta 2, it becomes 75.6 degrees Celsius and this becomes 30.6 degrees Celsius. Now, what is the LMTD? Theta m is equal to, the formula is theta 2 minus theta 1 divided by natural log of theta 2 by theta 1. So theta 2 minus theta 1, 30.6 minus 75.6 divided by natural log of 30.6 divided by 75.6. If I will calculate it, it comes around 49.75 degrees Celsius. Okay, so this question mark is also over. So only unknown remains as U. So what is U? U is equal to Q upon A theta m. What is Q? Q is 28753 28753.33 divided by, what is A? A is given 0.17. 0.17 and what is the LMTD? 49.75. If I will calculate it, overall heat transfer coefficient is 3399.74 watt per meter square degree Celsius or Kelvin. Okay, so this is the answer. Okay, now we'll see the problem number 15. Let's write the data. A chemical specific heat. First identify which type of problem it is. Parallel flow heat exchanger. Parallel. So draw the temperature profile for parallel. Both the fluid should enter from the same side. So this is TH1, this is TH2, this is TC1, this is TC2. Difference between these two is theta 2. Difference between these two is theta 1. Okay. So this is parallel heat exchanger. Now I will make a two column. One is for hot fluid and other is for cold fluid. Okay. A chemical specific heat 3.2 We don't know chemical is hot fluid or cold fluid. Let's read the problem further. Enters a parallel flow heat exchanger at 150 at a flow rate of 30,000 kg per hour. Still no idea. Cooling water, that means cold fluid is water. So naturally chemical is what? Because there is only hot fluid and cold fluid, na? So cooling water means water is definitely a cold fluid. So naturally chemical comes as hot fluid. So we got that idea. Specific heat of cooling water is how much? Cp, cold fluid, water is Cpc is 4.187. I will convert directly in joule per kg Kelvin by multiplying by 1000. 4187 joule per kg Kelvin. Now I understood chemical is a hot fluid. So it is what? 3.2 kilojoule per kg. So Cp of specific heat of hot fluid is, I will convert in joule, 3200 joule per kg Kelvin at 150. It is hot fluid. So Th1 is what? 150 degrees Celsius. At a rate of 30,000 kg per hour. It is a rate of chemical and chemical is hot fluid. So m dot h is equal to 30,000 kg per hour. So convert this is in second. So it comes around 8 point divided by 3600. So 8.3333 kg per second is the m dot h. Cooling water enters the heat exchanger at 20 degrees Celsius. So Tc1 is how much? Cold. I am writing from cold fluid side. 20 degrees Celsius. So Tc1 is 20. Th1 is 150. So this also I will put here. At a flow rate of 1000 kg per minute, it is the rate of cooling water. So m dot c 1000 kg per minute, but I don't want minute here, I want second. So 1000 divided by 60, it comes around 16.66 kg per second. So m dot c is also there. Heat transfer area, as it is a common thing, I will write here area is equal to 12 meters square. It is nothing to do with hot and cold fluid. It is the dimension of heat exchanger. So better to write it separately. Don't write under the columns. Overall heat transfer coefficient, that is also nothing to do with this 1000 watt per meter square Kelvin. This is the common data. Find the effectiveness of heat exchanger. So what is the required answer? The required answer is number 1 effectiveness epsilon, number 2 outlet temperature of both chemical. So Th2, chemical is hot na, the outlet temperature of hot fluid is Th2, and cold water, water is cold fluid. So what is the outlet temperature of cold water? Tc2. So these three things are asked in the problem. Now just look at the problem. First question you need to ask is which approach I should use, LMTD approach or effectiveness NTU approach. It's very easy to understand because in every problem more or less I repeated it. If 3 or 4 temperatures are known to you, you can use LMTD approach because that is the best approach. Even you can use epsilon NTU also, but LMTD method is the easier one, and that's why we are using it. But if 2 temperatures are known and 2 temperatures are unknown, in that case compulsorily you have to go by effectiveness NTU approach, that is epsilon NTU approach. You can't solve the problem by LMTD method. So though it is easy, LMTD is easy, we can't use that when 2 temperatures are unknown. So this is the case. In this problem, Th2 and Tc2 are not given. That means you can't use LMTD approach. You have to go by epsilon NTU approach. So for that, what to do? So this problem is effectiveness NTU approach. Why? Why? Because both two temperatures are unknown. Okay, so LMTD method can't be used here. So how to do it? So very first process is you need to calculate CH, heat capacity of hot fluid. It is a product of m dot h into Cph. Heat capacity of cold fluid, it is a product of mass flow rate m dot c into Cpc. So let's do it. What is m dot h? What is m dot h? M dot h is given as 8.4 times 3. 8.4 times 3. Just 1 minute. I have written it about this. I have to remove. Into what is Cph? Specific heat of hot fluid, that is given as 3.2 kilojoule. But I need in joule, so 3200. 3200. Now in the similar fashion for cold fluid, what is m dot c? 16.66 kg per second. And what is Cpc? 4187. It is 4.187, but better to use in, you have to use in joule. 4187. So if I will calculate it, it comes around CH 26,666.56, and this comes around 69,755.42. Now out of these two, CH is, if I am comparing this value, CH is less than CC. Therefore C minimum is, जो छोटी है, that is C minimum, CH, and C max is, and C max is, जो बड़ा है वो C max is CC. Okay, so by that way C minimum is equal to CH. CH means 26,666.56, and C max is how much? 69,755.42. Now we will get the value of R. R is called as heat capacity ratio. Heat capacity ratio, and that is C minimum upon C maximum. So how to get C minimum? It's already known to you. 2666.56 divided by 69755.42. R value is coming at 0.3822. What is R? It is heat capacity ratio. So I have calculated R. Now the next job is to calculate number of transfer unit. It is denoted by NTU. The formula of that is UA upon C minimum. So let's check it, whether we know U, whether we know A, whether we know C minimum. So U is known to you. Yes, U is given as 1000. Area is also known, 12. So U is 1000, area is 12, and C minimum just now calculated 26,666.56. I will get the answer of NTU as 0.45. If I know number of transfer unit NTU and heat capacity ratio R, I can easily go for effectiveness. So effectiveness of the heat exchanger is given by, now it is which type of heat exchanger? Parallel. For parallel flow heat exchanger, effectiveness is given by the formula 1 minus e raised to minus NTU 1 plus R divided by 1 plus R. So this is the formula in terms of heat capacity ratio R and number of transfer unit NTU. I know R, I know NTU. So I will go step by step. First I will calculate NTU 1 plus, okay, wait a minute. First I will calculate 1 plus R. So 1 plus R is equal to 1 plus, what is R? R is calculated at 0.3822. 0.3822. So what it becomes? 1.3822. 1 plus R. Now I will get the product of NTU 1 plus R. NTU 1 plus R. What is NTU? 0.45. And what is R? 1 plus R? Just now calculated, 1.3822. So this answer comes as 0.6219. 0.6219. Now I will go for e raised to minus NTU 1 plus R. So e raised to minus 0.6219. If I will calculate it, it comes 0.5369. Okay, now I will go for epsilon is equal to 1 minus. If we are doing this in number of steps, you will not get wrong in the final calculation. If you are trying to substitute directly and trying to do at once in a single step on calculator, there may be a mistake. So better to go step by step, just like me. 1 minus, now I can put this value I already know. I have calculated here, see. So it becomes easy now, 0.5369. Total divided by 1 plus r is also known to you, 1 plus r. 1.3822, 1.3822. So answer comes at 0.3350. So this is the answer of effectiveness and it is answer number 1. Now what is our next target? Our next target is determining exit temperature of hot and cold fluid. Both are unknown. So how to get that? If I know effectiveness, I can use another formula of epsilon. What is the another formula? Delta T. For this already we have used. Delta T for C minimum fluid divided by maximum temperature difference, that is TH1 minus TC1 for heat exchanger. So what is the C minimum fluid? Tell me. C minimum is 26,666. This is for hot fluid. So hot fluid is a C minimum fluid. तो hot fluid का temperature difference क्या है? डेल्टा T TH1 माइनस TH2. अगर कोल्ड फ्लूइड का होता ये C मिनिमम, अगर कोल्ड फ्लूइड का होता तो आप क्या करते हैं? यहाँ TC2 माइनस TC1 करते. बट अगर आप ये देखोगे, यू लुक एट हियर, minimum value out of these two is 26,666 and that is for what? That is for hot fluid. So hot fluid is a C minimum fluid जिसका हीट कैपेसिटी मिनिमम है. तो हॉट फ्लूइड का टेम्परेचर डिफरेंस क्या आएगा? TH1 minus TH2. So that I have written here, and maximum temperature difference is TH1 minus TC1. So let's use this formula. I know epsilon. Epsilon is 0.3350. I know it. 0.3350 is equal to TH1. What is TH1? 150 minus TH2. TH1 is 150 minus TH2 is unknown, and TH1 minus TC1. What is TC1? TC1 is 20. So that is the benefit of writing on the diagram. And if I will solve this, the answer of TH2 comes around 106.44 degrees Celsius. Okay, this is TH2. Now this one exit temperature I got. Now I need to know the second exit temperature. This I got for hot fluid. Now I want to know it for cold fluid. That can be calculated by heat balance equation. M dot S Cph TH1 minus TH2 is equal to, for cold fluid, M dot C Cpc TC2 minus TC1. So this I can modify as Q is equal to M dot S Cph is heat capacity. It is CH. TH1 minus TH2, and M dot C Cpc is a specific heat capacity for cold fluid, Cc, capital Cc. It is Tc2 minus Tc1. So I know CH value. What is CH? CH is 26,666.56. TH1 minus TH2. What is TH1? 150. TH2 just now calculated 106.44. What is CC? CC is from here 69,755.42. 69,755.42. TC2 is unknown, minus TC1 is 20. If I will calculate this, I will get the answer of TC2 as 36.65 degrees Celsius. So this is answer 3. Now students, will go to the next problem. I think it is problem number now 16. Let's write the data by interpretation. A parallel flow heat exchanger. So I will do it here parallel. Draw the temperature profile for parallel flow. Both fluids are entering from the same side, that is left side, and exit from right side. So here is TH1, here is TH2, this is TC1, this is TC2. Difference between these two is theta1 and difference between these two is theta2. Designed to cool oil. कूलिंग किसका होगा? हॉट फ्लूइड का. सो इसका मतलब हॉट फ्लूइड क्या है? ऑयल है. अभी मैं नेक्स्ट कॉलम में जाता हूँ, कोल्ड फ्लूइड. लेकिन कूल ऑयल का डेटा दिया हुआ है. ऑयल इज हॉट फ्लूइड, क्योंकि कूलिंग किसका होगा? हॉट फ्लूइड का होगा. तो ऑयल इज हॉट फ्लूइड एंड उसका डेटा है CPH, specific heat of hot fluid. It is given in kilojoule, so I will multiply by 1000, so it becomes 2100 joule per kg Kelvin. And mass flow rate m dot I will attach, because oil is hot fluid, so m dot h 20 kg per minute. So 20 kg per minute, if I will divide by 60, because minute 60 second, so 20 divided by 60, it is 0.3333 kg per second. From 70 डिग्री सेल्सियस टू 40 डिग्री सेल्सियस. तो टेम्परेचर यहाँ कम हो रहा है. किसका टेम्परेचर कम होगा? हॉट फ्लूइड का कम होगा नेचुरली. सो TH1 इज हाउ मच? 70 डिग्री सेल्सियस. TH2 किस? 40 डिग्री सेल्सियस. सो आई विल पुट इट हियर 70 and this is how much? 40. By using cold water, so cold fluid is what? Water. And उसका CP कितना दिया हुआ है? 4.2. So CP of cold water, CP of cold fluid is equal to, this is in given in kilojoule, so I will convert in joule, 4200 joule per kg Kelvin. And m dot of cold water means m dot C I will attach, 50 kg per minute. So 50 divided by 60, that comes around 0.8333 kg per second. And what is asked to you? What is asked to you? Required answers. Required answer number 1, area of the heat exchanger, that is size. In exam, size oblique area, anything can be asked. Size of the heat exchanger means calculate area. Area of the heat exchanger means also calculate area. So that's why I have put here size oblique area of heat exchanger. And outlet temperature of water and effectiveness. Outlet temperature means outlet temperature of water. So TC2 is asked. Water is a cold fluid, so TC2 is asked. And number 3, effectiveness is asked, epsilon. Now if I will see the temperatures, I am knowing only by using cold water available at 30 degrees Celsius. So cold water inlet temperature is also given 30 degrees Celsius. TC1 is 30 degrees Celsius. So whole data is completed now. Now, how to approach to this problem? If you see the data, out of 4, 3 temperatures are given to you. So if 3 or 4 temperatures are known to you, you can use both the methods. But which one is the easier method? LMTD method. So I will go by LMTD approach for this problem. In last problem, two temperatures are unknown. So we don't have any another option to go for epsilon NTU method. But in this case, out of three temperatures are known, I can use LMTD approach because it is easier. So I will go to the solution. If I want to know the area, I can use the formula Q is equal to UA theta m. This is the basic equation in LMTD approach. UI AI theta m or U0 A0 theta m. As the tube dimensions are not given, these two formulas get discarded. Only this formula remains into picture. So if I want to know A, I must know Q, I must know U, and I must know theta m. So our target is to get Q, U, and theta m to get answer of A. So let's start with Q. What is Q? M dot H, CPH, TH1 minus TH2. I am writing heat balance equation for hot fluid. Now for cold fluid, M dot C, CPC, TC2 minus TC1. Okay. Now choose any one out of these depending on data. I know M dot H, I know CPH, I know TH1 and I know TH2. I can't go for this because TC2 is unknown. That is asked to you. So I will use this combination. Q is equal to M dot H 0.3333. 0.3333. What is CPH? 2100. What is TH1? 70 minus 40. 70 minus 40. I will get the answer of Q as 20997.9 watt. But this can be utilized. Now I can use Q is equal to M dot C, CPC, TC2 minus TC1. This Q answer I can utilize to get the answer of TC2. 20,997.9 is equal to M dot C. What is M dot C? 0.8333. 0.8333 kg per second into what is CPC? 4200. What is TC2? That is unknown. And what is TC1? 30 degrees Celsius. 30. If I will solve this, the answer of TC2 comes as 35.99 degrees Celsius. Okay. Now, I think I got the answer of Q. So this question mark is already over. Okay. Now I will calculate U. I will calculate U. Just check whether U is given to you. This data I have not written. Heat transfer coefficient on water and oil side. Water side. So H, it is inside or outside not mentioned. So anything you can take inside, anything you can take outside. So I will take HW as 400 watt per meter square Kelvin, and H oil I will take it as 200 watt per meter square Kelvin. Anything you can take, H inside and H outside, no problem. So how to get the U? If you remember students, in previous problem where the dimensions of the tubes are not given, in that case the formula of 1 upon U becomes 1 upon Hi plus 1 upon Ho. If the dimensions of the tube are not given and the thermal conductivity of the tube is not given. So this is the basic formula. So how to use it? 1 upon Hi. You can take anything as inside and anything as outside. You are having a freedom. So I will take 1 upon 200 plus 1 upon 400. 1 upon 400 plus 1 upon 200. You can take anything as inner and outer, no problem. So if I will solve this, I will get the answer as answer for U is 133.33 watt per meter square Kelvin. So I got the answer of U also. So two question marks are over. Now to get area, only one question mark is remaining, theta m. So what is theta m? LMTD. For that you require the value of theta 1 and theta 2. So what is theta 1? Look at the diagram. Theta 1 is TH1 minus TC1. TH1 minus TC1. Theta 2 is TH2 minus TC2. TH2 minus TC2. Just put the values. TH1 minus TC1. 70 minus 30. And TH2 minus TC2. TH2 is 40. And TC2 is calculated here. 35.99. So 70 minus 30 is 40 degrees Celsius. Okay. And this is 4.01 degrees Celsius. So what is LMTD theta m? Theta 2 minus theta 1 divided by natural log of theta 2 by theta 1. Solve it just by putting the values. 4.01 minus 40 divided by natural log of 4.01 divided by 40. If I will solve it on the calculator, it comes at 15.64 degrees Celsius. So now all the question marks are over. Only unknown is A. So what is A? A is equal to Q by U theta m. So what is Q? Q is how much? 20997.9. 20997.9. What is U? 133.33. It is calculated here. And what is theta m? Just now calculated 15.64. 15.64. So the answer is answer of area is 10.06 meter square. I have already calculated for you. So this is your answer number 1. Now what is the next target? Next target is to get TC2, but it has already achieved. You check it. Somewhere in between I have already calculated TC2. So this is answer number 2. Answer number 2. Now only remaining thing is epsilon. Only remaining thing is epsilon. So how to calculate epsilon? If I am using a LMTD approach, I can use the basic formula of effectiveness by definition. Epsilon is equal to delta T for C minimum fluid. C minimum fluid divided by maximum temperature difference TH1 minus TC1. Now how to get C minimum fluid? How to identify it? So let's calculate heat capacities of hot and cold fluid separately. What is heat capacity? It is a product of mass flow rate into specific heat of hot fluid. Similarly for cold fluid I am writing. Just put the values. M dot H 0.4 times 3 into 2100. 0.4 times 3 into 2100. And M dot C, it is 0.8333 into what is the specific heat of cold fluid? 4200. If I will calculate it, the first value comes as 699.93 and the second value comes at 3499.86. Now out of these three, which is lesser? CH is less than CC. So CH becomes C minimum and CC becomes C maximum. So CH is how much? 699.93 and C max is 3499.86. Okay, so this is C minimum and this is C maximum. Now epsilon is equal to C minimum is what? Hot fluid, CH. CH means heat capacity of hot fluid. So hot fluid. So what is the delta T for hot fluid? TH1 minus TH2 divided by maximum temperature difference TH1 minus TC1. So let's put the values. TH1 minus TH2, 70 minus 40 divided by TH1 is 70 minus TC1. TC1 is 30, 30, and the answer of epsilon is 0.75. So this is your answer. So students, that's it for today. We'll see remaining problems in the next lecture.